Hi everyone. So good afternoon here, good afternoon to all. So first of all, let me know whether audio and video are clear. Is audio and video are clear here? Yes or no? Is audio and video everything is clear? Yes? Yes. Okay. Okay. So I hope it is clear here. Okay, fine. Okay. So today, we are going to see a concept in magnetostatics here. We are going to see a concept in magnetostatics. Okay. So we are going to see a concept in magnetostatics. See, in case of prelims here, IAS prelims exam, okay. So most of the questions here, will be very much conceptual and basic questions, okay. So most of the questions will be theoretical also. Whereas in GATE you are going to have some application oriented, problem oriented, okay. But in IAS exam, engineering services, the questions will be very much conceptual and it will be mostly theoretical questions here, okay. So today I am going to discuss one topic, that is Lorentz force equation. Today we are going to discuss about Lorentz force equation that is present in magnetostatics topic, okay. Okay, yeah, fine. So today we are going to see about Lorentz force equation for B field here, Lorentz force equation for B field, okay. See here, first of all, here we are going to deal with magnetostatics here. This topic will come under magnetostatics. See here. So always here, the magnetism is caused by moving charges, and magnetism is also felt by what? Magnetism is also felt by moving charges. Yes or no? See, what do I mean by this statement is, what I am saying here is, magnetism is caused by moving charges and the magnetism is also felt by what? Is also felt by only moving charges. So what do I mean by this statement? Means, see here, suppose if you consider a stationary charge here, if you consider a stationary charge, whenever you place a charge here, it is going to set up some electric field in its vicinity, right? Okay, it is not going to produce any magnetic field. Okay, so that means a stationary charge cannot produce any magnetic field. It is going to set up only electric field in its vicinity, right? Okay, so now if you consider the charge is moving with uniform velocity here, if suppose the charge is moving with uniform velocity, suppose the charge is moving with uniform velocity. Okay, what happens here? So whenever the charge is moving with uniform velocity, it is going to produce what? It is going to produce current. Yes or no? So whenever charge is moving with uniform velocity, we call it as what? We call it as current, right? Okay. So whenever charge is moving with uniform velocity, it is going to produce current. So whenever current is flowing here, so it is going to set up what? It is going to set up the magnetic field surrounding it or not? Yes or no? So what is the source for this magnetic field here? It is not a stationary charge, it is a charge that is moving with uniform velocity. So what is causing this magnetism here? It is not the stationary charge. What is causing? Only moving charge is causing the magnetism. So that's what I have said. Magnetism is caused by what here? Magnetism is caused by moving charges, right? Okay, so that point you can note here. Okay, so you can note that point here. So what is that point I have said? Magnetism is caused by moving charges. Magnetism is caused by moving charges. Right, okay. So and also what I have said here, this magnetism is also felt by only moving charges here. This magnetism is also felt by only moving charges. So what do I mean by this statement? So here what I am saying here? Here I am saying magnetism is also felt. Magnetism is also felt by moving charges, is also felt by only moving charges. So what do I mean by this statement? See, if suppose take a magnet here, let us consider this is north pole, and here let us consider south pole. Okay, so the magnetic field lines will always point from north pole to south pole. The magnetic field lines will always point from north pole to south pole here, right? Okay, so now here if you place a charge q here, if you place a charge q, some stationary charge q in the magnetic field, so this field is nothing but what here? B field. Okay, B field, that is magnetic field. So whenever you place a stationary charge in magnetic field, it is observed that this charge is not experiencing any force here. So whenever you place a stationary charge in magnetic field, it is not going to experience any force. So whereas if you place a current carrying wire here, if you place a current carrying wire in the magnetic field, so current carrying wire means what here? The charge carriers are moving within the conducting material, right? Okay, so that means it is nothing but moving charge carriers, right? Okay, so whenever you place a current carrying wire in the magnetic field, it is observed that this current carrying wire is experiencing what? Is experiencing the magnetic force, is experiencing magnetic force. It is experiencing magnetic force. Right? Okay. So that means a stationary charge is not experiencing any magnetic force, whereas a current carrying wire, that means a moving charge, is experiencing what? Is experiencing a magnetic force. So that means magnetism is also felt by what? Magnetism is also felt by only moving charges. That means only moving charges can feel the magnetic force. Stationary charges cannot feel the magnetic force. Right? Okay. So these two statements are very, very important here. These two statements are very, very important. Okay. So what are they here? Magnetism is caused by moving charges, and magnetism is also felt by what? Is also felt by only moving charges. A stationary charge cannot produce magnetic field, and a stationary charge cannot feel the magnetic force. Right? Okay. So these two statements are very, very important. Next here. Next. Is it clear here? Is it clear? So I hope it is clear here. I hope it is clear. Next. Okay. Sir, you said whenever you are having a moving charge, it is going to experience a magnetic force. So can we have any equation that is going to give you the force experienced by a moving charge in magnetic field? See, what I have said is whenever you are having a moving charge in a magnetic field, it is going to experience some force. Moving charge is going to experience some force. So what is that force? Okay, so that force is given by Lorentz force equation here. That force is given by what here? Lorentz force equation. That force is given by Lorentz force equation for B field. So this is called as Lorentz force equation for B field. Lorentz force equation for B field. So what is that force? See here. So the magnetic force I am representing with FBR. Okay, the magnetic force is equal to Q into V bar cross V bar, V bar cross B bar. So this is called as Lorentz force equation for B field here. Whenever you are having a charge Q, whenever you are having a charge Q kept in whenever you are having a charge Q moving with velocity V, kept in magnetic field B is going to experience a magnetic force F, right? Okay, so this is magnetic force here. Okay, this is magnetic force. So whenever you are having a charge moving with velocity V kept in magnetic field B, it is going to experience a magnetic force, right? So that force is given by this equation, and this equation is called as what here? Lorentz force equation. This equation is called as Lorentz force equation, right? Okay, now see here, now you can see from this equation here, whenever you place a stationary charge, its velocity will become what? Its velocity will become equal to 0. So whenever velocity becomes 0, the force is also going to be what? The force is also going to be 0, right? Okay, so a stationary charge cannot experience any magnetic force. Yes or no? Okay, okay here. So now see here I can write the same expression in this manner here. I can write the same expression in this manner. See here how I can write the same expression. See here. Now F bar is equal to Q into so V bar is nothing but velocity here. V bar is nothing but velocity. So that velocity I can write it as what? Displacement by time. Yes or no? So this velocity I can write it as displacement divided by time. So cross B bar. So now here from here what I can get here? Here Q by T here. So I am taking T outside. So Q by T I can write it as what? I can write it as current. Yes or no? So current I into what? I into L bar cross what? L bar cross B bar. L bar cross B bar. So that means whenever you place a current carrying wire, of length L in magnetic field B, it is going to experience what? It is going to experience a magnetic force. It is going to experience a magnetic force, right? Okay, okay, yeah. So you can represent in this form, or you can represent in this form here. Both are correct. Understood? Okay. Now here, what are the observations that we can make from this Lorentz force equation is, see here, if you consider electric field here, if whenever we are studying electric field, so there the force is given by what here? The force on a charge is given by what? F is equal to what? F is equal to E into Q. F is equal to E into Q. Right? Okay. So this equation is also called as Lorentz force equation for electric field, and this equation is called as Lorentz force equation for magnetic field. So whenever we are having both the fields, that means electric field as well as magnetic field, then you have to write the Lorentz force equation for both electric field as well as what? Magnetic field. Okay. Okay. So now see here. So now if you observe this equation here, see the direction of the electric field, the direction of force, the direction of electric field and the direction of electric force, both are pointing in the same direction. Both are going to point in the same direction, right? So the direction of electric field and the direction of electric force, both are pointing in the same direction. Now coming to here. Now here, this is magnetic force. Right? Okay. So this is magnetic field. So what is the direction of magnetic force and what is the direction of magnetic field here? Both are pointing in the same direction or both are perpendicular to one another? Tell me. See here, for example, let us consider the velocity is in x direction. Let us assume the velocity of the charge is in x direction, right? And the magnetic field is pointing in y direction. Let us assume the magnetic field is pointing in y direction. Then what is the direction of the force here? What is the direction of the force? So this component is along x direction, this component is along y direction. So if you do the cross product, that is ax cap cross ay cap, ax cap cross ay cap, you are going to get what? Az cap. That means the direction of the force in this case will be what? Will be in z direction. Right? So that means the direction of the force, the direction of the magnetic force and the direction of the magnetic field. The direction of magnetic field is in y direction here. The direction of magnetic force is in z direction. That means both are what? Both are perpendicular to one another. The direction of the magnetic force and the direction of magnetic field, both are what? Both are perpendicular to one another. Yes or no? This is very, very important here. Right? Okay. Whereas in case of electrostatics, electric field, so the direction of field and the direction of force both are in the same direction. When coming to the magnetostatics, the direction of field and the direction of force both must be perpendicular to one another. Both are perpendicular to one another, right? Okay, okay, yeah, fine. Okay. Next, okay. Okay, yeah. So I will ask you one question here. I will ask you one question. See, that is, if suppose if you are having a current carrying wire here, if you are having a current carrying wire, sir, you are saying whenever you are having a current carrying wire, it is going to set up magnetic field in its vicinity. But inside the current carrying wire, the charge carriers are flowing. So because of that charge carriers, there is any possibility for electric field in the vicinity of this current carrying wire? See, what I am asking is, if you are having a current carrying wire, the charge carriers are flowing inside the current carrying wire. Since the charge carriers are flowing inside the current carrying wire, due to the charge carriers, is there any chance for the electric field to exist in the vicinity of this current carrying wire? So this is my question here. Okay, so tell me the answer here. Is there any possibility for the electric field to exist surrounding the current carrying wire? Yes or no here? See here, actually when I am saying a current carrying wire here, whenever I am saying current carrying wire, so it is a neutral conductor or not? Yes or no? It is neutral, right? Yes or no? It is neutral. The number of charge carriers, number of electrons and the number of protons that are present in a conducting wire are same. So that means it is going to behave as what? Neutral conducting material. But the nature of conductor is it can allow the charge carriers to move freely. So whenever you apply a force across this conductor, that means you connect some battery or something, okay, so then it is going to drive the charge carriers. Within the conducting material. Right, you are not supplying the charge carriers from outside here. It is going to drive the charge carriers within the conducting material. Right, okay. So that means this conducting material, the current carrying wire is a neutral. It is nothing but a neutral here. So that means a neutral wire cannot produce what? Cannot produce the electric field. Yes or no? For the electric field to produce, there must exist what? There must exist charge. Here you are having negative charges as well as what? Positive charges. The net charge will be equal to what? The net charge will be equal to 0. So if the net charge is equal to 0, it cannot produce any electric field. Right? Okay. So there will be no electric field in the vicinity of what? In the vicinity of current carrying wire. Okay. So this current carrying wire, this is nothing but what? DC current here. This is DC current. Steady current. Right? Okay. Okay. Yeah. So this is generally students will ask this type of doubts here. So that's why I have explained here. Right? Okay. So now coming to this Lorentz force equation. See here. Okay. So I said the force direction and B field direction both are perpendicular to one another. Right? Okay. Okay. Yeah. So now. By using this Lorentz force equation here, okay, we can they can ask some conceptual questions. So what type of questions they can ask? We will see that. If suppose they may give you that there are two current carrying wires. Carrying the current in the same direction. If you are having two current carrying wires carrying the current in the same direction, then they are going to attract each other, or they are going to repel each other, or they are not going to exert the forces on one another. So like that they may ask you the question, or they may ask you like, if you are having two current carrying wires and the current if you are having two current carrying wires carrying the currents in opposite directions, then those two current carrying wires are going to attract each other or repel each other, or they are not going to exert any forces on one another. Okay, so like that they can frame the questions here. Okay, so all this type of conceptual and theoretical questions you can answer from this Lorentz force equation with the help of this Lorentz force equation. Okay, see here. See, whenever if I consider a current carrying wire here, if I consider a current carrying wire, let us say it is carrying the current in upward direction. It is carrying the current in upward direction. So in which direction it is going to set up the magnetic field? We know that the B field is going to set up. The B field is going to set up. That means the B field is going to circulate. Around this current carrying wire. Yes or no? The B field is going to circulate around this current carrying wire. Right. Okay. So whenever you are having a current carrying wire, it is going to set up a B field, and that B field is going to circulate around this current carrying wire. Okay. So in which direction it is going to circulate? In which direction it is going to circulate? Yes or no? So that is given by right hand rule here. That is given by right hand rule. So what you have to do is always take your right hand. So point the thumb along current direction. Yes or no? So then enclose curl your fingers here. Yes or no? Okay. So the direction in which you are enclosing the fingers, right hand, 4 fingers, will give you what? Will give you the direction of what? The direction of B field. So the current is flowing in upward direction, and the B field is going to circulate around the wire. That is given by what? That is given by these 4 fingers. Yes or no? So here current is flowing like this. So the B field is going to circulate around this wire in this manner. So that means it is going to circulate. In this manner. Right? Yes or no? It is going to circulate in this manner. So that means here on this side, if you consider on this side, okay, on this side it is going into the board. Yes or no? This loop is like this. So on this side it is going into the board, field is going into the board. On this side of the wire, the field is coming out of the board. So here I am representing that here. So the B field is pointing into the board here also into the board, here also into the board. On this side it is pointing out of the board, on this side it is pointing out of the board, on this side it is pointing out of the board. So in this manner the B field is circulating around this current carrying wire. Right? Okay. Now if I consider a current carrying wire like this, let us say it is carrying the current I. Okay, so like this. Now if the current is flowing in this direction here, then how the field lines are going to circulate around the wire? It is going to circulate like this or not? Yes or no? The field lines are going to circulate in this manner. Right? Okay, they are going to circulate in this manner. So now if you want to know the field direction, what you have to do? So point the thumb along what? Along current direction. So if you point the thumb along current direction, wait. If you point the thumb along current direction, above this wire, the B field is going to point out of the board, and below this wire, the B field is going to point into the board. So they are coming like this here. Yes or no? This is current carrying wire. So the B field is going to circulate around this wire like this. Yes or no? Okay. So above this current carrying wire, it is coming out of the board. Below this current carrying wire, it is going into the board. Yes or no? If the current is flowing in this direction, the B field is going to circulate like this around this wire. So here it is coming out of the board. Below this wire, the current is going into the board. If suppose the current is flowing in this direction here, then you have to point the thumb. In this direction. Then the field is going to circulate. In the direction of the field in which, that means what I am saying here. In order to determine the direction of the field, you have to enclose the fingers. Around this thumb here. Okay, so that means the field lines are going to circulate like this. Yes or no? So above this wire, it is pointing into the board. Below this wire, it is going to point out of the board. Okay, so I hope it is clear here. I hope this convention is clear. Yes or no here? Yes or no? Okay. 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 So whenever the current is flowing in this direction, above this wire, the B field is going to point out of the board, and below this wire, the B field is going to point into the board. Okay, the B field is going to be like this, right? So the B field is going to point out of the board here, into the board here, out of the board here, into the board here, out of the board here, into the board here, like this. So the field lines are going to point like this. Yes or no? Okay. So they are going into the board here, and here they are coming out of the board. Here they are going into the board and out of the board. So in this manner, the B field is going to circulate around that wire here. Okay. Similarly, if you consider a current carrying wire, if it is carrying the current in this direction, above this line, that means above this wire, the B field is going to point into the board. Above this wire, the B field is going to point into the board, and below this wire, the B field is going to point out of the board. Yes or no? It is going to circulate like this. It is going to circulate like this. Okay. So here it is going to come out of the board, and here it is going to into the board. Okay. So it will be like this here. It will be like this. So this is how the B field lines are going to circulate around the current carrying wire. So I hope it is clear here. I hope it is clear. Yes or no? Okay, yeah. Okay. So now see here. So now we will determine whenever we are having two current carrying wires carrying the current in the same direction, whether they are going to attract each other or repel each other, or they are not going to exert any forces on one another. So that's what we want to determine here. Now see here. Let us consider a current carrying wire. So let us say it is carrying the current I1. It is carrying the current I1 in this direction here, in this direction. Okay. So just now I have told that whenever you are having a current carrying wire, it is going to produce the B field. So above this wire, it will be out of the board. Below this wire, it will be into the board. So here the B field is pointing, here the B field is pointing, below the wire the B field is pointing into the board. I am not representing above the wire here. Above the wire it is coming out of the board. Anyway, if you want, you can represent. It is going to come out of the board, right? Okay. So this is the B field. This is the B field produced by what? Produced by this current carrying wire I1. This is the B field produced by current carrying wire I1. Okay. So it is coming like this. Okay. It is coming out of the board here, and it is going into the board like this, right? Okay. Okay, yeah, fine. Okay. Next. Now what I am doing here is, now I am placing a current carrying wire here. I am placing another current carrying wire in this magnetic field B1. So this B1 is produced by I1. Okay. So now I am placing a current carrying wire in this B field. Produced by I1. So I am placing another current carrying wire in this B field here. And let us say it is carrying a current I2. So we know that whenever you place a current carrying wire in the B field, it is going to experience what? It is going to experience magnetic force or not? Yes or no here? It is going to experience magnetic force, right? Okay, it is going to experience magnetic force. So in which direction it is going to experience the magnetic force? So that we can determine from Lorentz force equation. Now let us consider this axis here. This axis, let us consider this as x-axis, and in this direction let us consider y-axis. This as x-axis, this is y-axis, and z-axis is going to come out of the board. Yes or no? So if you curl your fingers from x to y, z-axis is going to point out of the board. So z-axis is coming out of the board. This direction is x-axis and this direction is y, right? Okay. Okay. So now see here. Now apply Lorentz force equation here. So Lorentz force equation is equal to what? F is equal to I into what? I into L bar cross B bar. Now you have placed a current carrying wire. I2. you have placed a current carrying wire I2 in the magnetic field. In the magnetic field produced by what? Produced by current carrying wire I1. Produced by current carrying wire I1. Yes or no? So you have placed I2 in the B field, produced by I1. So that means this B is nothing but what here? B is nothing but B1, right? Okay, so now here L bar here, L bar is nothing but displacement. L bar is nothing but displacement of charge carriers. Now here the current is flowing in this direction, means the charge carriers are moving. The charge carriers are moving in this direction. The charge carriers are moving in this direction, right? Okay, so the charge carriers are moving in this direction means this displacement, they are displacing in this direction. That means along X direction, along X direction. So this displacement you can consider along what? This is along X direction. And this B field here, B field is pointing into the board. Yes or no? This B1 is pointing into the board. Into the board means which direction here? Out of the board is positive Z. Into the board means what? Negative Z direction. So B field is pointing, this B field is pointing in negative Z direction here. Negative Z direction, right? Okay. So it is pointing in negative Z direction. Now here displacement is in X direction and the B field is in negative Z direction. So what is the force direction here? What is the direction of the force? Tell me, what is the direction of the force? See, this is in X direction, that is, let us take AX cap cross, and it is in negative Z direction, that is minus AZ cap. So AX cap cross minus AZ cap, what you are going to get? AX cap cross AZ cap, AX cap cross AZ cap will be minus AY cap, and here you are having minus, minus into minus will become plus. So you are going to get AY cap, you are going to get AY cap. So that means the force direction here, the force direction will be in positive Y direction. Yes or no here? Yes or no? So the force direction will be in positive Y direction. That means this I2 wire here, this I2 current carrying wire is going to experience a force, in which direction? In positive Y direction, that is in upward, direction like this, right? Okay, okay here. Now okay, so now forget about this I1 here. Now forget about this I1. Okay, forget about this I1. Forget about this I1 and forget about this B1. Forget about this B1. Now consider only I2 here. Consider only I2. So whenever you consider I2, so the current is flowing. The I2 current is flowing in this direction or not? That means in along X direction. Along X direction. So point the thumb along X direction. Then the field produced by I2. The field produced by I2 is going to point in which direction here? Above this wire. Above this wire it will be out of the board, and below this wire. Below this wire it will be into the board. Right? So this I2 is going to produce the B field such that above this wire the B field is going to come out of the board, and below this wire the B field is will go into the board. Right? Okay. So this B field, this I2 is going to produce the B field. Is going to produce the B field. Is going to produce the B field. Let us say. Okay, this I2 is going to produce the B field above the wire. Above the wire it will come out of the board, below the wire it will go into the board. So above the wire it will come out of the board. Yes or no? So this B field, this I2 is going to produce the B field above the wire. Above the wire the B field it will come out of the board. Okay, so this is nothing but B2 here. This is nothing but B2. That is produced by I2. That is produced by I2. So now here I am placing. Now here I am placing a current carrying wire. We are having already current carrying wire or not? So I am placing a current carrying wire I1 here. Now I am placing a current carrying wire I1 in this B field. In this B field. So whenever I place a current carrying wire I1 in this B field, it is also going to experience the force or not? It is also going to experience the magnetic force. Now in which direction it is going to experience the force here? So same equation here, F bar is equal to I1. Now the current carrying wire is I1. It is placed in magnetic field B2. It is placed in magnetic field B2. So I1 into L bar cross what? L bar cross B2. Okay. So now here the displacement of charge carriers is along which direction here? Is along x direction. So this displacement is along x direction, and this B field is coming out of the board. This B2 is coming out of the board. Yes or no? So it is coming out of the board means it is pointing in positive z direction. So that means it is in positive z direction. B field is in positive z direction. So if you do Ax cap cross Az cap here, if you do Ax cap cross Az cap, what is the direction you are going to get? Ax cap cross Az cap will give you what? Minus Ay cap, will give you minus Ay cap. That means it is going to experience the force. It is going to experience the force in which direction here? Negative y direction. It is going to experience the force in negative y direction, right? Yes or no here? It is going to experience the force in negative y direction. So that means this current carrying wire here, this current carrying wire I1 is going to experience the force, in negative y direction. It is going to experience the force in negative y direction. So that means here this current carrying wire I1 is producing the magnetic field B1, and whenever you place I2 in this magnetic field, it is going to experience the force in positive y direction. In the same manner, this I2 is going to produce the B field here. Yes or no? It is going to produce the B field that is coming out of the board here. If you place a current carrying wire I1 in this B field, it is going to experience the force in negative y direction. So this current carrying wire I2 is experiencing the force in upward direction. This current carrying wire I1 is experiencing the force in downward direction. That means these two are what here? These two are attracting each other. These two are attracting each other. So that means what we can conclude, whenever you are having two current carrying wires, whenever we are having two current carrying wires carrying the current in the same direction, they are going to attract each other. They are going to attract each other. Okay. So note down that point here. Note down that point. Now here, similarly, if I consider two current carrying wires, carrying the currents in opposite directions here, So here also you can do the analysis in the same manner here. Okay, if you do the analysis in the same manner, you are going to get the force experienced by I1 is going to point in upward direction, and the force experienced by I2 you are going to get in downward direction. So that means they are repelling what? They are repelling each other. Yes or no? So whenever you are having two current carrying wires carrying the currents in the opposite direction, you can do the analysis in the same manner here. You are going to get what? We are going to get here I1 is going to experience the force in positive y direction like this, and I2 is going to experience the force in negative y direction like this. So that means they are repelling each other. Okay, you can do the analysis in the same manner here. Okay, and you can prove that, right? Okay, so you can do that analysis here on your own. Okay, so now you can write these two statements. Here. So what are the statements here? So whenever, or you can write simply like this: two current carrying wires carrying the current in the same direction, will attract each other. So that means there will be a attractive force between those two current carrying wires. Okay, so similarly, two current carrying wires carrying the current in opposite directions, directions will repel each other, will repel each other. So that means the force between them is repulsive force here. The force between them is repulsive force. So whenever they are carrying the current in the same direction, they are going to attract each other, and if they are carrying the current in opposite directions, they are going to repel each other. They are going to repel each other. Right? Okay. Okay, yeah. Okay. So these points are important here. These points are important. We can expect the questions directly on these statements in engineering services. Okay, right? Okay. Next here. So this is Lorentz force equation. So I into L bar cross B bar, or you can write F bar is equal to Q into V bar cross B bar, V bar cross B bar, right? Okay. So these are the Lorentz force equation, Lorentz force equation. Now here, if suppose, okay, so if suppose a charge is moving here, a charge is moving in the B field with velocity v, with uniform velocity v. So whenever the charge is moving here, whenever the charge is moving in B field with uniform velocity v, then if I ask you what is the work done, by the B field, what is the work done by the B field on this moving charge? See, what I am asking is what is the work done, by the B field on this moving charge, So whenever you are having a charge that is moving with uniform velocity in magnetic field, then what is the work done? If you want to determine the work done by the B field on this moving charge. Okay, so how to determine here? We know that work done is nothing but what? Work done is nothing but force dot what? Force dot displacement. Okay, so do force dot displacement here, that is F bar dot what? F bar dot L bar. So that is equal to what? That is equal to I into L bar cross what? L bar cross B bar. I can use this equation or this equation. Both are same here. Okay, so I into L bar cross B bar dot what? Dot L bar. So this is the work done. By the B field on the moving charge. Moving with uniform velocity v. Right? Okay. So what is the work done you are going to get? Tell me. See, whenever you are doing force dot displacement, this is nothing but work done here. So what is the work done you are going to get? Tell me here. What is the work done you are going to get? See here. Let us assume the displacement is in x direction, and let us assume the magnetic field B field is in y direction. So then ax cap cross ay cap will be az cap. That means the force direction will be in z direction, and the displacement direction is in x direction, right? Okay, or you can say here the displacement is in x direction. Okay, if you do this, what you are going to get? Tell me what you are going to get. Here the force direction. So the force direction is given by this term here, yes or no? The force direction is in z direction, and this L bar, this displacement is in x direction, So if you do force dot displacement, what you are going to get? Force is in az cap direction, displacement is in x direction, yes or no? So both are perpendicular to one another or not? Both are perpendicular to one another. So that means force dot displacement, what you are going to get? You are going to get 0. So that means the work done by the B field on the moving charge. The work done by the B field on the moving charge is always equal to what? Is always equal to 0. Right? Okay. So that's what we have proved here or not? Yes or no? So always force dot displacement, we are getting what? We are getting 0, because the force direction is always perpendicular to what? Is always perpendicular to the displacement direction. So that's why we always get the work done is equal to 0. Work done is equal to 0. So what is the consequence? What is the consequence of work done is equal to 0? So what happens if work done is equal to 0? See here, now whenever the charge is moving here, whenever the charge is moving in B field, whenever the charge is moving in B field, so the work done by the B field is equal to 0. The work done by the B field on that moving charge is always equal to 0. So what do you mean by that? What do you mean by that? So see, that means, see here, if suppose for example here, for example, a person is running here, a person is running with uniform speed here, a person is running with uniform speed, let us assume. Okay, now if suppose if I push that person, that means I am doing some work on that person, I am doing some work on that person. So whenever I do some work on that person, then what will happen here? His speed is going to change or not? Yes or no? So he is running like this. If suppose if I push that person, his speed is going to change because I have done some work on that person. Or if suppose if I pull that person in backward direction, he is running like this, I am pulling that person like this. Yes or no? So then in that case what will happen? His speed is going to decrease, his speed is going to decrease because I am doing the work, I am doing the work on that person. So that means whenever you do the work, on a moving person, the speed of that person is going to change or not? The speed of that person is changing. So in the same manner, whenever a charge is moving with uniform velocity, whenever a charge is moving with uniform speed here, whenever a charge is moving with uniform speed, okay, since the work done is equal to 0, that means the B field is not going to change the speed of the moving charge. Why here? Because it is not doing any work, on the moving charge. That means the speed of the moving charge will remain same, it is not going to change. So that means this B field will neither increase the speed of the moving charge nor decrease the speed of the moving charge, right? Okay, so the charge will continue to move with the same uniform speed, right? Okay, so why means the work done by the B field on the moving charge is always equal to 0. So that means the charge speed neither increases nor decreases. It cannot change the speed of the moving charge. But what it can do here? It can at most change the direction of the moving charge. Yes or no? See, on the moving charge, it is on the moving charge, whenever you are having a moving charge, it is experiencing some force or not? It is experiencing some force. But the work done by the field on the moving charge is equal to 0. That means this B field is not going to alter the speed of the moving charge. But what it can do is it can at most change the direction of the moving charge. So how it is changing the direction of the moving charge? All those things we are going to see here. Okay, so write down this statement here. So since work done by the B field, on the moving charge is equal to 0, since the work done by the B field on the moving charge is equal to 0, implies that it cannot alter the speed, of the moving charge. Implies that it cannot alter the speed of the moving charge. But it can at most change the direction. Of the moving charge. Okay, so since the work done by the B field on the moving charge is equal to 0, is equal to 0 implies that it cannot alter. It means what here? Here it means B field here. Here it means B field. Okay. So it cannot alter the speed of the moving charge, but it means here B field here. It means here B field, right? Okay. So but the B field can at most change the direction of what? Change the direction of the moving charge. It cannot alter the speed of the moving charge, but it can at most change the direction of the moving charge. Okay. So how it is changing the direction of the moving charge? How it is changing the direction of the moving charge? So that's what we are going to see now. That's what we are going to see now. Okay. So it cannot change the speed of the moving charge, right? It can at most change the direction. It can at most change the direction of the moving charge, right? Okay, yeah. Okay. So is it clear here? Is it clear? Sir, Roshan, sir, please reply. What you are asking, sir? ESE में सिक सर्जरी लोड है, ESE का प्रिपरेशन करना सही रहेगा. I have done sick. Even I don't know here, what do you mean by LASIK surgery? Okay, see Roshan, you can join my Telegram channel here. There I can resolve your queries. Okay, you please join my Telegram channel. So I will reply there. Okay. Okay. Okay, so work done by B field on moving charge is equal to 0 implies that B field cannot alter the speed of the moving charge, but it can at most change the direction of the moving charge. So how it can change the direction of the moving charge? That's what we are going to see now. That's what we are going to see now. Okay. 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 Yeah. So now here let us consider this is y-axis. Let us consider this is y-axis, and let us consider this is x-axis. Let us consider this is x-axis, right? Okay. Now here I am considering B field here. I am considering B field that is pointing. The B field is pointing into the board here. See, actually field that is pointing into the board, you are going to represent like this. You will represent like this, right? Okay. So the vector is pointing into the board means you are going to represent like this. But I am not putting this circle and all here. I am just representing in this manner. You have to understand that the B field is pointing into the board, right? Okay. So here the B field is pointing into the board. B field is pointing into the board. So this is B field here. So B field is pointing into the board. Right. Okay. So this is nothing but B field here. This is nothing but B field. This is nothing but B field. So now I am going to show you whenever there is a moving charge in B field, what I said here, B field is not going to alter the speed of moving charge, but it can at most change the direction of the moving charge. So how it is going to change the direction of the moving charge, that's what I am going to show here. Now here this is B field here. B field is pointing into the board. Into the board means what here? Into the board means what? along negative z direction, right? It is x direction, it is y, so z is coming, positive z axis is coming out of the board, positive z axis is coming out of the board, that means negative z is going to point into the board. So here B field is pointing in negative z direction here, B field is pointing in negative z direction, right? Okay, yeah, fine. So now let us consider a charge q. Let us consider a charge q is moving along x direction. Let us assume initially a charge q is moving along x direction, yeah, is moving along x direction like this. So whenever a charge is moving along x direction in a uniform B field, then it is going to experience what? It is going to experience the force. So that force is given by what? That force is given by F is equal to what? F is equal to Q into V bar cross B bar. F is equal to V into Q into V bar cross B bar, right? So now here the charge is moving in which direction here? X direction. So that means its velocity is in which direction? Its velocity is in x direction. Its velocity is in x direction, right? And B field is pointing in which direction? Negative z direction. B field is pointing in negative z direction, right? Okay, so B field is pointing in negative z direction. So what must be the direction of force? So in which direction this charge is going to experience the force? Here it is Ax cap cross Az cap here. Ax cap cross Az cap will give you minus Ay cap, and here you are having minus into minus will become plus, right? So that means it is going to experience the force in positive y direction. See here, this is Ax cap cross A minus Z cap here. You are going to get plus Ay cap direction. That means this force is going to experience the force in y direction. So whenever the charge is moving in x direction, it is going to experience a magnetic force. It is going to experience a magnetic force in y direction. Yeah, it is going to experience a magnetic force in y direction, right? Okay, so whenever the charge is moving like this, so it is experiencing the force. It is experiencing the force in y direction. It is experiencing the force in y direction. So whenever something is moving like this here, so if you try to pull that object, towards you like this, yes or no? Let us say some person is moving like this here, and you are trying to pull that person towards you, yes or no? So he is running like this and you are trying to pull like this. So then he is going to take what? He is going to take a curved path or not? So he is running with some uniform speed like this. So if you try to pull that person in this direction towards you, then he is going to take what? He is going to take a curved path, right? He is not going to move, he is not going to come directly towards you, yes or no? He is going to take some curved path, right? So in the same manner, whenever a charge is moving like this, so a force is pulling that charge, a force Fy, that is magnetic force, is pulling that charge in positive y direction. So whenever it is pulling the charge in positive y direction, that charge is going to take what? Is going to take some curved path. It is going to take some curved path and tries to move, and finally tries to move along y direction. Now here the charge is moving in positive y direction. Here the charge is moving in positive y direction. So whenever the charge is moving in positive y direction, then in which direction it is going to experience the force? So F is equal to Q into what? V bar cross B bar, right? Okay. Now here the velocity of the charge is in y direction. And what is the B field direction here? B field direction is along negative z. So what you are going to get here? Ay cap cross what? Ay cap cross minus Az cap. What you are going to get here? Ay cap cross Az cap is Ax cap. Here you are having minus, so that means you are going to get minus Ax cap. You are going to get minus Ax cap, right? So that means the force it is going to experience is in minus x direction, negative x direction. So that means this charge whenever it is moving in y direction, it is going to experience a magnetic force in which direction here? In negative x direction, right? Okay. So same here, same scene. Now it is trying to move in this direction, and a magnetic force is trying to move the charge towards what? Towards negative x direction. So what will happen here? What will happen? This charge is going to take what? Is going to take a curved path and try to move along which direction here? Negative x direction. Now it is moving along negative x direction. So whenever it is moving along negative x direction, then in which direction it is going to experience the force? So that's what we have to write now. Okay. So F bar is equal to again Q into V bar cross B bar here, V bar cross B bar. Now tell me here, in which direction it is going to experience the force? Now the velocity is in negative x direction, and B field is in negative z direction, here minus, minus into minus will become plus, ax cap cross az cap will become minus ay, so it is going to point in negative y direction, so it is going to experience the force, in negative y direction. Right, it is going to experience the force in negative y direction. Okay, so now the same thing here. So it is moving like this. The force is trying to pull the charge towards what? Towards negative y direction. So what it will do here? It is going to take a curved path and tries to move along y direction, Now it is moving along negative y direction. Right. Okay. So whenever it is moving along negative y direction here, then in which direction it is going to experience the force? So F bar is equal to Q into what? Q into V bar cross what? V bar cross B bar. Now the velocity is in negative y direction. B field is in negative z direction. Here minus into minus will become plus, ay cap cross az cap will become what? Ax cap. So the direction of force will be in positive x direction. Yes. Okay. So it is going to experience the force in positive x direction. So then it is going to trace the path. Then it is going to take the curved path and tries to move along positive x direction, right? Okay, so in this manner the charge is going to trace a circular path here. This is nothing but a circular path. So it is going to trace a circular path whenever it is moving in what? It is moving in B field. Okay, so here the radius of this circular path, is let us say r. The radius of the circular path is let us say r. Right. Okay, so that means whenever so whenever the charge is moving in B field, yes or no? So at each and every location here, the speed of the charge is not changing. What is changing? The direction of the charge is changing. Yes or no? So that's what I have said or not? So whenever a charge is moving with uniform speed in a B field, that B field is not going to alter the speed of the charge, but it can at most change the direction of the moving charge. Yes or no here? So it is changing. Here it is moving like this, so it has changed the direction like this. Here it has changed the direction like this. Yes or no? So it is changing, this B field is changing the direction, of this moving charge, but it cannot change the speed of the moving charge. Right. Okay. Now here what you have to observe here is, now the B field is pointing in which direction here? In negative z direction. B field is pointing in negative z direction, and the velocity of the charge carrier here, the velocity of the charge is present in which plane here? Now here it is moving in x direction, here it is moving in y direction, here it is moving in negative x, here it is moving in negative y, like this. Yes or no? So that means the velocity of the charge here, is in xy plane. Yes or no? The velocity of the charge is in xy plane, and the magnetic field is in negative z direction. The velocity is in xy plane and the B field is pointing in negative z direction. That means what is the angle between the velocity of the charge and B field here? The velocity of the charge is in only xy plane. That means it is going to have only x and y components, right? And B field is in negative z direction. Yes or no? So that means the angle between here, in this case, the angle between angle between B field and angle between B field and velocity. Angle between B field and velocity is how much here? Is theta is equal to what? Is equal to 90 degrees. Is theta equal to 90 degrees. So whenever the angle between the velocity and B field is 90 degrees, then the moving charge is going to trace what? Is going to trace a circular path. It is going to trace a circular path in the plane that is perpendicular to what? That is perpendicular to B field. So whenever the angle between the velocity and B field, is 90 degrees, in that case the charge is going to trace a circular path in a plane that is perpendicular to what? That is perpendicular to B field. So this is the plane or not? This is the plane in which it is tracing the circular path. This plane is perpendicular to what? This plane is perpendicular to B field. Right? Okay. So this point is very, very important here. This point is very, very important. So note down that point here. Note down this point. So when theta equal to 90 degrees. So what do you mean by theta equal to 90 degrees? It is the angle between what? It is the angle between V bar and B bar here. V bar and B bar. So when theta equal to 90 degrees, the path traced by the path, or I can say when theta equal to 90 degrees, the charge Q is going to trace the circular path, in a plane. It is going to trace the circular path in a plane perpendicular to what? In a plane perpendicular to B field. Yes or no? Okay. So this point is also very, very important here. So whenever the angle between V bar and B bar is 90 degrees, the charge Q is going to trace what? Is going to trace the circular path in a plane that is perpendicular to what? In a plane that is perpendicular to B field. Right? Yes or no here? See here, this is not ZX plane here. This is XY plane. This is X axis. This is Y axis. This is XY plane. Z axis is coming out of the board. Positive Z axis is coming out of the board. Negative Z axis is going into the board. Right? Yes or no? Okay. Okay. Okay, fine. So now we try to determine the radius of this circular path here. So what is the radius of this circular path here? How to determine the radius of this circular path? Tell me. How to determine the radius of the circular path? See here, how we can determine here is, see, the charge is moving along this circular path. So whenever the charge is moving along this circular path, a force is trying to pull, this magnetic force, yes or no? This magnetic force is trying to pull the charge towards the center, yes or no? So whenever a particle is circulating along a circular path here, a force will try to pull that particle towards what? Towards the center. That force is nothing but what here? Centripetal force. Yes or no? That force is nothing but centripetal force. Now here, this magnetic force is trying to pull the charge. Towards the center of the circular path. Yes or no? So that means this magnetic force itself is acting as what here? Is acting as a centripetal force. Yes or no? Okay. So that means this magnetic force must be same as what? Is acting as centripetal force. So what is the formula for centripetal force here? Centripetal force is nothing but what? See here, the force F is equal to what? F is equal to mv square by r. Where m is the mass of the charge, v is the velocity, and r is the radius of the circle. Yes or no? So this is centripetal force. right? Okay, so what I am saying here, this magnetic force itself is acting as what? Is acting as centripetal force. So that means I can equate the magnetic force to centripetal force. Yes or no? So what is this magnetic force here? What is this magnetic force? Why I am equating the magnetic force to centripetal force? Because the magnetic force itself here is acting as what? Is acting as centripetal force, right? So what is the magnetic force you are going to get? That is nothing but Q into V bar cross B bar here, V bar cross B bar, right? Okay. So that is V bar cross B bar means I can write it as what? I can write it as VB into sine theta. Yes or no? So V bar cross B bar means I can write it as what? VB sine theta. VB sine theta. Here theta is equal to what here? Here theta is equal to 90 degrees. So substitute here theta equal to 90 degrees. So this is equal to mv square by r. mv square by r. Right? Okay. So now here V will get cancelled. Sine 90 will become 1. So what you are going to get? QB is equal to mv by r. mv by r. So therefore the radius of the circle here. Therefore the radius of the circle. Therefore the radius of the circle is what here? R is equal to what? R is equal to mv by qb. R is equal to mv by qb. So this is the radius of the circle. This is the radius of the circle traced by what? Traced by the moving charge. Traced by the moving charge Q in the B field. In the B field. Yes or no? Now here, what is the angle here? What is the angle? When it is going to trace the circular path, whenever theta equal to 90 degrees here, whenever theta equal to 90 degrees. If theta is not equal to 90 degrees, that will become another case here. There it is going to trace helical path and all. Okay, so that we can see later here. But here, when theta equal to 90 degrees, it is going to trace what? It is going to trace the circular path, and the radius of that circular path is nothing but what? Is nothing but mv by qb. Is nothing but mv by qb. Right? Okay. Okay, yeah. So is it clear here up till here? Is it clear? So these are the applications or concepts of Lorentz force equation here. Lorentz force equation, right? Okay. So they can ask you some conceptual or theoretical questions from this Lorentz force equation. Okay. Okay, yeah. So I hope it is clear here. I hope it is clear. Is it clear here up till now? Yes or no here? Okay, so I hope it is clear here. So with this, I'm going to wind up this session here. Okay, so tomorrow at the same time 4 p.m. we are going to start. We are going to continue this EMT lectures here. Lectures on EMT. Right? Okay. So tomorrow at 10 a.m. I'm going to take the session for analog electronics here, and at 4 p.m. I'm going to handle EMT. Right? Okay. Okay. Yeah. So today I'm winding up the session with this. Okay. Tomorrow we are going to start some other topic in EMT, right? Okay. Okay, yeah. So I hope everything is crystal clear here. Okay. Okay, yeah. Okay, then I hope it is clear. Okay, yeah. So then take care guys, take care, bye bye.